Welcome to the ENME 351 video lecture series. This is part one of a two-part installment on transistors. This lesson focuses on the bipolar junction transistor. Transistors really form the heart of all the digital logic material that we've covered in this course. And for a mechatronic system, a transistor is often used to control a larger voltage or a current that you might need for an actuator for your system, say something like a motor. And so there are a variety of reasons that you might implement a transistor even beyond the digital logic that we've explored previously. So let's take a look at transistors, and we'll begin with the BJT transistor, the bipolar junction transistor. A BJT is formed based on a diode. Recall that a diode has an N-type silicon region that's doped with something like phosphorus or arsenic, and thus it has extra electrons floating around. This is then pressed up right against a P-type silicon. And P-type silicon, that's doped with something like boron. In this sense, it's effectively missing electrons, so it has holes that can be filled in. So the combination of these two, that creates our PN junction, and that creates what we would typically think of as a diode. To create a bipolar junction transistor, on top of this PN junction, we'd add another layer. So we could add a P-doped layer that would create a PNP transistor. Or similarly, we could add an N-doped layer, creating an NPN transistor. So the two different types of BJT transistors we can create then are the NPN transistor and the PNP transistor. The symbols for both transistors look fairly similar, the only difference here being that for the NPN transistor, we have an arrow here, and for the PNP transistor, we have our arrow up here. We see that these are three-terminal devices, and the first terminal, which is ultimately going to control the performance of the transistor, that's what we call the base. The emitter is always the side with the arrow on it, and the collector, that's going to be the third terminal. We'll also define here a few currents that are of interest to us. First, we have IB, that's the current going into the base, and then we also have IC. In both cases, for the NPN transistor, I see that current is flowing from the collector down to the emitter, and for the PNP transistor, I see is flowing from the emitter down to the collector. And then finally, we have the voltage between the base and the emitter, and we'll define that as VBE, B for base, E for emitter. And for the PNP, we also label this VBE, even though the emitter will have the higher potential. There are other metrics we could also define, such as VCE, the collector-emitter voltage. But what you see on the screen here, those are the primary metrics, primary currents and voltages that we are going to define to describe the performance of these BJT transistors. The key thing to remember for the BJT transistor is that it's effectively a current-controlled switch. So the current flowing from my collector down to my emitter, IC, that's going to be driven by the current flowing through the base here in conjunction with this potential here, VBE. The other key feature of these BJT transistors is that I can have a small base current, and that'll control a very large collector current. This is effectively giving me a current amplification, or sometimes you might see it written as a gain. We'll typically write this in terms of a beta or an HFE. This is really key for our mechatronic systems because often we have a small current coming out of our digital logic device, something like our Arduino, and I might want that to control a large current that I'd be using to drive a load such as a motor. So by using this three-terminal BJT, I can have a small current going into this device, and that can control a very large current coming from the collector down to the emitter. If we think about the BJT as a current-controlled switch, then we need to consider how to turn that switch on and off. So let's create a table here, and we'll look at the NPN and the PNP transistor, and we'll figure out how to turn them on and off respectively. The key to this on-off process is going to be this voltage, VBE, the voltage difference between the base and the emitter. And we can think of this effectively as a diode. Recall that an NPN bipolar junction transistor looks like this. We have N-doped silicon next to P-doped silicon next to N-doped silicon. So these are effectively two diodes back to back. So recall for a diode, we could plot our IV curve, and at some point, some voltage here, we have our turn-on voltage. And that turn-on voltage for a silicon diode, that's typically about 0.6 to 0.7 volts. So this transistor then, that's going to be in the off state if VBE is less than 0.6 volts. If that's the case, then our base current will be approximately 0, and our collector current IC will be approximately equal to 0. The same thing holds for the PNP transistor. However, now VBE is defined from the emitter down to the base. But the same is true in this case. If VBE is less than 0.6 volts, our base current IB is going to be approximately 0, and our collector current IC is going to be approximately 0. So in both of these cases, our transistor is off. So now let's take a look at how we turn on the transistor. To turn on the transistor, we need to get that base emitter voltage equal to this turn-on voltage. So our NPN transistor will be on in the case where VBE is approximately equal to 0.6 volts. So in this case, we'll have a base current greater than 0, and we'll have a collector current much greater than 0. Since the BJT is a current amplification and current amplifier results in a current gain, any small current coming through the base is getting amplified, so I have a much larger current going through my collector. And the same holds for the PNP transistor. In the case where we have a base emitter voltage, it's about 0.6 volts. And of course here the potential is actually from the emitter down to the base. In that case, we'll have a current flowing through the base, so IB will be greater than 0. And again, our collector current will be much greater than 0. Now, on for a transistor is not as simple as it sounds in terms of a standard switch. So let's take a look at the on behavior for a BJT transistor. Let's consider here an NPN transistor with a base emitter voltage of about 0.6 volts. So my transistor is in the on state. Here we'll plot the collector current as a function of VCE, the voltage between my collector and emitter. For a small base current, a plot of the collector current versus VCE might look something like this. As I increase my base current, I might have a resulting IC versus VCE curve that looks like this. And these curves will continue to increase in terms of the collector current as I continue to increase my base current. Right off the bat, we see some interesting behaviors in terms of our plot. And to help illuminate some of these behaviors, let's draw a line of demarcation. So above this line here, I'm ending up with an amplification of my base current up to my collector current, and we'll refer to that again as beta. So this will be our current gain. So if I'm in this region then, we call this the linear region, I'm going to have a relatively uniform, relatively linear current gain. So I can easily predict based on some input base current what my output collector current is going to be. However, when I'm in this region to the left of my line, say when I'm down here, right, if I have a relatively small change in the base current, well, the collector current is not changing very much. And in some cases, it would even be difficult to identify a change in the collector current at all. And so this region to the left of the line here, that's referred to as the saturation region. It's also typically defined as having a small collector-emitter voltage drop, a small VCE. And where this behavior really comes into play is in the cases where we're using a transistor as a switch. So if we use the transistor as a switch instead of just a basic current amplifier, then I'm going to want a small voltage drop across my transistor. So I'm going to want to operate in this saturation region where I have a small VCE in the case where I'm using the transistor as a switch. To illustrate this, let's take a look at the circuit here where I'm using a transistor to switch the current going through a motor. So using this setup, I could, for example, turn the motor on and off. So using this transistor as a switch, I want the maximum voltage drop possible across the motor such that the voltage drop between my collector and emitter, VCE, is as small as possible. And so a great rule of thumb to operate in that saturation region is to have my current gain somewhere around 10, right? So if we're in the linear region, we're getting up to 50 or 100. So if we want to make this VCE as small as possible, a good rule of thumb is to have that ratio of the collector current over the base current of roughly about 10. By implementing this rule of thumb, we'll end up with a VCE on the order of about 0.2 volts. So if I set up my circuit then to get this current gain of about 10, I'll find that my voltage drop across the resistor is 0.2 volts, which is fairly small for a BJT transistor. Let's run through a quick example then where we use a BJT transistor to drive a motor. In this setup, I'm going to say that the resistance of the motor is relatively high, so it's about 100 ohms. And here we have an NPN transistor that'll be used to control the collector current, which will ultimately control the current through the motor, driving such things as the torque of the motor. And so we're really interested in determining what is the required value of this resistor right here. So what is that value such that I can put this transistor into saturation and most effectively switch the motor on and off? Let's assume that we are controlling this transistor using an Arduino. So our Vin will be 5 volts. And we know that if we're in saturation, then VCE is going to be approximately 0.2 volts. So VCE here, that's 0.2 volts. And we'll go ahead and define Vmotor as 10 volts. With this setup, I see the collector current. That'll be equal to Vmotor minus VCE over the resistance of the motor, which is equal to 10 minus 0.2 over 100, or 98 milliamps. Using our rule of thumb, if we want our transistor in saturation, then IC divided by IB needs to be equal to about 10. Thus, I need a base current equal to IC over 10, or about 9.8 milliamps. To turn the motor off, we'll set Vin coming from the Arduino equal to 0 volts. As a result, VBE will be less than 0.6 volts. So we'll have no current going through the base and thus no current going through the collector, or in other words, no current going through the motor. And when we turn the motor on using an Arduino, right, we'll send Vin to 5 volts. And thus we can now calculate the current through the base. So IB will be equal to Vin minus the voltage associated with the diode drop, so VBE, divided by R. So that'll be 5 minus 0.6 volts over R is equal to 9.8 milliamps. And this tells me then that I need a resistance R of approximately 450 ohms.